I can try to talk this way. Oh, okay. Sorry about that. Okay, so in any case, and he was thinking outside the box. He was thinking that we would probably should not focus on these the classical observables such as the position of the electron, or the speed or momentum of the electron, and so on and so forth. Rather, look at the observables, and therefore he developed some new aspect. So, and after his formulation, of course, there was matrix quantum mechanics, and he said, not only is the universe a stranger than we think, it is stranger than we can think. That's so we should accept this the aspect and think about this outside the box. Feynman also made a statement saying that the quantum mechanics describes the nature as observed from the point of view of common sense, and yet it is fully agrees with the experiment. Therefore, we should just accept nature as she is observed. Okay. So, in fact, after 100 years, we have understood this quantum mechanics to a high precision level already. Anticipating a broader audience, I want to have some introductory materials and to put everybody on the same page. The title is about high energy physics. So high energy physics, by definition, we are thinking about the higher energies than normal and necessarily relativistic. We are probing shorter distances. Think about the small particles and necessarily the quantum mechanics. So therefore, if we merge relativity and quantum mechanics, we're getting into the relativity quantum mechanics. Of course, we're written down by Klein-Gordon equation for spin zero and written down by Dirac in the spin half of this fermion, the relativity of quantum mechanical functions. But this applicability is very limited, because those are supposed to be a quantum mechanical single particle description. However, we know that once we get into higher energies, the mass is not conserved the quantum number. So the energy, mass is energy, energy is the mass, and you produce more than just one particle easily. So therefore, we need to go beyond this one. The applicability for these equations are very, very limited once you get into energies. That's what we do. So of course, in terms of the language connection to our condensed matter colleagues, we need to have the creation and annihilation operators. So that way we write down this the so-called second quantization. So we write down this the creation operator to produce a particle with a definitive momentum and probably definitive spin as well. So once you have the spin and the momentum, this is the conserved quantum numbers under the Poincare environments. Right? So that's our description. So now, of course, we have a different species in the spin zero, spin one, and we can define the number, the particle number operator and the total energy or the Hamiltonian operator. This is what our current description. And this is the field. So that's why we formulate this theory in terms of our standard language now standard language into quantum field theory. So this is what we do. Okay. But so in connection with this observed behavior, so then Feynman said, and also Heisenberg said, and including the so-called the wave particle, the duality and uncertainty principles, all these things are built in our formulation. For example, we can create a particle with a definitive energy or momentum here, but in that case, we would not be able to tell the particular position, right? This is a superposition. The other function is a superposition for all different momentum. And then if you have a definitive momentum here, and then it's a wave here. It's no particular definition position anymore. So this is a built-in framework for all this quantum mechanical behavior, including this the original difficult place to understand the wave particle duality and so on and so forth. We're talking about a collection of quanta and also space-time functions. Okay. So of course, we can formulate in different ways. The Feynman formulate this according to the classical path. We integrate the overall particle classical path from this action, and the action is formulated from our theoretical Lagrangian. So that's our more common language to use. And then of course, you can calculate the physical processes using this intuitive approach we call the Feynman diagrams according to perturbation theory. So overall, so this is our description starting from the ground state, and the ground state is not nothing. Vacuum is not nothing, but all the quantum mechanical effects should come in. So now let's come to this the example. Suppose we calculate the quantum effect from some ground state, like from the leading order. Then if we are able to expand this according to some perturbation parameters such as coupling, and then this in quantum mechanics, even the first level quantum mechanics course will tell you the perturbation theory to expand according to the other quantum states, the corrections. And in this case, we're summing over the intermediate states, and in our field theory language, we are inserting the quantum corrections at the one loop level. That's what we say. But you can continue on to include higher order corrections, and then this is equivalent to our two insertions. It's a two loop corrections. Okay, then you integrate over all the contributing diagrams, and those are the quantum effect. In fact, those are the quantum effects so genuine. It's really the uncertainty principle to tell you that we are probing different energy scales integrated over all the possible contributing states with a different momentum. Remember, momentum will be the one to specify the quantum states. So for momentum and the total angular momentum. So therefore, so we're able to predict these things. And so of course, the best example probably would be the QED calculation. And direct relativity quantum mechanics, as we said, has a very limited application applicability. So then we need to extend into the quantum form, including the creation and annihilation, as well as this, the quantized electromagnetic field. Now, of course, this was the establishment of this quantum field theory to be able to predict the calculations. The best example is the magnetic dipole moment. Of course, we know this was Schwinger's the first calculation to establish the formalism to do the renormalization. Of course, we all know that his atome even prints this major contribution alpha over 2 pi electromagnetic the fine structure constant over 2 pi, and this is the deviation. So far, if we continue to predict this within the framework quantum the quantum field theory, it's up to 5 to 6 loops in QED already for the electron. I think there's a 1/2 missing here. But here, the electron prediction versus the direct measurements is up to 10 to the 10 digits, 10 to 11 digits there already. This is the most accurate quantum theory in science, in nature. So I want to, the reason I want to go this far is to tell my audience, testing quantum mechanics, this is the best place we have ever demonstrated. It's not only about the quantum mechanical correlation and so on and so forth. That is my topic I want to get into. But this is the place we have the most convincing test for quantum mechanics and also the prediction beyond the quantum mechanics formalism and also including the particular model here. Yes. No, there's quantum calculations, right? It's good. No, that's your particular model, particular theory. But formalism, in terms of quantum mechanical formalism, you use the perturbation theory. I showed you the one loop, two loop, right? Yeah. Yeah, no, that's not anymore. No, not anymore. No. Yeah, so I think the fractional quantum Hall effect is more sensitive. Right. Similarly, even you go slightly above the electron mass, only 200 times more higher than the electron mass, we get into muon G minus 2. And then it involves much more, much richer physics than the QE. Then in fact, it gets into the even the weak. Of course, QCD is a dominant one, as we all know. And from the recent announcement of only a few weeks ago, and the Fermi-lab measurements were finalized, and it's seemed to be in reasonably good agreement. Well, still possible interpretation beyond this standard model, but it tells you the power that the quantum mechanics formulation is worked. And within the standard model, it's accurate up to 10 to the 6 digits, 10 to 6 and 7 digits already. The point I want to make is this is the place to put the quantum mechanical framework into our particular theory and model, and everything seems to be adequate. So that is basically my introduction. Okay. Now let's get into the real topic of this the collider data. So this is a disclaimer. Most people, I think, somewhat still misinterpret this our kind of a work about the quantum tomography at the colliders. We are not testing quantum mechanics there anymore. We want to apply quantum mechanical principle, quantum field theory, to go beyond this testing. Testing was done at other places, much better, orders of magnitude better in the testing place. It's not the testing quantum mechanics. It's misconception to say we test quantum mechanics. It's even not. Because the original EPR sense has a lot of subtlety correlation and philosophical interpretation. We have the loopholes in our collider data, period. So there's no loophole free test for this EPR anyway. First of all, and secondly, it's not even my goal. It's not even my goal to test the EPR in the quantum mechanical data. Instead, what we want to do, we have the largest amount of data at the LIC, at the colliders. And it's a quantum mechanical. It's built in. There's no reason not to look into this data to see the quantum information instead. Okay? Not testing quantum. We're not going to overthrow quantum mechanics at all. I just don't. Not only I don't expect that. Secondly, there's nothing. Point is that the built-in quantum information there. Let's see what we can learn. What we can do. So that is basically our goal. We will be able to construct the observables, the standard quantum mechanical observables. Correlations built in our basic elements all the time anyway, from Schroeder, it's there. And then we want to dig out the entanglement observables, Bell observables, and many other quantum information quantities such as Discord, magic, and so on and so forth. I will give you a few examples. Those examples are nothing new from our field theory calculations, but new construction to lead into some interesting correlation, interesting properties. So that's what we want, basically. So hope to establish quantum tomography in 3 dimensions and understand quantum nature and probably even predict certain things may even have some sensitivity to BSM. So I don't claim that the quantum observables would be better to discover BSM physics. I don't think that's the case. I don't think that's there yet, but it should be there anyway. Once you have BSM, our prediction in terms of our standard model prediction, you will see the difference anyway. It's built in. It is there. Okay, so let's go back to the square one, the correlation. The correlation exists all over places. This is a famous one that Bell first pointed out. It's Bertelmann's saw. Okay, and I think Professor Bertelmann is still around, and he was such an interesting iconic figure, and he would always prefer to wear his socks in different color. It's always one pink. Okay, so then he wears his pink sock and some other color. But so this is a correlation. So this is a classical correlation. So once he walks into your office, and you see the pink, that otherwise not pink. Okay. So either he walks in forward, backward, or he hit one leg up, down, or left to right. It's the same. Once you see the pink, you know there's some other one. But quantum mechanically, this is not the case. If you have a spin half particle, you know the spin particle with the eigenvalue plus, and the other one. So if they have a two entangled state, it's one. Otherwise, it's okay. But if you want to do this from back to right, the left and right, and back forth, you cannot make a decision anymore. This is a fundamental feature of quantum mechanics, non-commuting the observable. That. So the quantum mechanical correlation or the entanglement is far beyond the standard correlation we experience on the data. So that is very interesting information. Okay, so the point is that if you are able to construct one particular state, bipartite, two spin half particles, you can form singlet or triplet But if one give you spin up, the -1 give you spin down, they are kind of separatable. So each state is behaving almost like a separate. You measure one would not really necessarily change the other. However, these two states entangle. These two states, if you measure one, the other one is fixed. But if you measure the other one with the opposite, the other one is also correlated. So this is not separable. That if you measure these in different directions, they give you the quantum mechanical entangled properties rather than the simple, just separable classical observers. So that is the major feature. And this feature is a built-in. This feature actually is a simple but fundamentally important to characterize the quantum effect. And all these so-called quantum information aspect, these are the key. Basically, you keep track of this. So that is what people construct. So in that case, the non-inseparable systems will encode this the entanglement. And if you are able to measure one, then the other one is correlated according to quantum mechanical predictions. It's not classical. Of course, that was proven by the real demonstration from experiments, and there was no loophole anymore by setting this the AMO measurements, and was won the Nobel Prize in 2022. So the experiment started from Alain and Asbach as early as 80s. So there are many. So the long history was interesting. In fact, Professor C.S. Wu, who established the parity violation experiment, she was one of the first ones. Was underappreciated as well. She, of course, she was as early as that the early time to establish to start these experiments. Anyway, so this is the quantum mechanical correlation was proven, and the Bell inequality violation was established, not the classical, and that was the reason that this finally get the prize. Honestly, I don't think it's a big deal. We had, I mentioned already, we had quantum mechanics 12 order 9. Actually, quantum mechanics. No classical correspondence anyway. Okay. But it's good to know this quantum information exists even in our real life AMO experiment and so forth. So that we want to march into the LIC data, collider data. Collider data, a large amount of collider data always encode information like this. So I think that's interesting to go into. Okay, quickly. So you can define a quantum state as we always do. You define a quantum state, and a generic doesn't have to be wave function. It's just generic quantum state, whatever conserved quantum numbers we have, and they give the quantum state. And we write down this density matrix a different way to write the particular state, define a particular state. And then you can calculate, you can measure any observables according to this formula. Okay. But if there's only one term, so we usually call it a pure. If you have probability sum over several factors there, we call this the mixed state here. But you can even write down this according to this the simple, in particular for spin half, you can even decompose that according to these Pauli matrices. We call it a qubit. Okay, the quantum bit, so qubit. So that is a direct analogous for many examples, such as spin half particles and the superconducting current and top quark, flavor, any quantum state with two quantum numbers, two level systems that you can parameterize in this way, including the flavor that I'm going to discuss toward the end. So all of these in principle can serve as the qubit to serve for your quantum computing in principle. So that's why we want to make connection with this. So now you have two of them. So then therefore you can introduce the entanglement. Then you have two of them. You decompose them into the 4x4 instead of a 2, and then you have this the one polarized state, second polarized state, and both polarized are correlated. So therefore, you have a 3 plus 3 plus 9, 15 parameters to describe fully describe this the bipartite states, polarization and correlation. This is what we call tomography. If you're able to measure these things, and you map this system out with 3 dimensions, XYZ dimension, even non-commuting. So this is what we are. This is the goal. That once you're able to perform the tomography measurements, you determine all these 15 parameters, 3, 3, 9. In particular, CIJ, the correlations. between the two spins. Once you're able to determine these 9 parameters CIJ, you have the full quantum information to calculate any observables, including the entanglement quantity and including Bell inequality violation, and so on and so forth. So the all quantum information is built in this. That's the tomography. And once again, it could be a spin, could be any other 2 level states. So the formalism is universal. So therefore, the Pauli matrices don't have to be spin spatial XYZ, and could be flip, could be any, as long as you have 2 level systems. So this is the one. I'm going to give you examples. Okay, so Pauli information here. So then you decompose these the separable and not separable states, and you can even construct the Bell state. So this was an original example that John Bell proposed to measure this more than just forward backward along the z direction, and because of non-commuting behavior, you measure at least 2 directions. 3 directions is better. You measure 2 directions. You construct this the combination of the angular momentum the quantities. Classically, if they are commuting, it's different, but it's non-commuting, and you have this. You establish this the inequality. This was the inequality he first proposed. There was a refined version, and for convenience and so on and so forth. All these give you the feature. If this is less than 2, that's classical observable, never go beyond. But larger than 2, it's a probabilistic quantum mechanical description beyond the commuting observable. And then there are many different observables to dig out the correlation and information that this is a list for a few representative quantities. And the Bell inequality is the most stringent test to only a very small corner that you can have this violation. And classically, you never violate this inequality. Then you can calculate other quantities like this is steering. Steering is very similar to these entanglements. It's also in certain region in entanglement, certain region you don't see the entanglement. And so then so each one is smaller, it's a stronger quantity to test the quantum correlation and behavior. This correlation is very broader, and then the magic. So I will comment on a few different features. So first of all, for example, concurrence is the easiest one that tells you the quantitative measure of entanglement, entangle or not. If in particular phase space, this is CIJ constructed quantity to be larger than 0, and that particular phase space is 2 states. If not, and you cannot decide whether this particular system is entangled or not. So then you can quantify this. And then this part, I mentioned to you already, this part tells you the quantum information, the total information versus the quantum information. So it tells you the whether you can mimic this by classical information or the quantum information. So you can define that way. And the magic measure the stableness. If this is totally stable, and the system has no advantage over classical quantities. So if you have something non-stability there, you have certain quantum mechanical behavior. So this is a measure of how this you can build up a quantum computer. Use this whether it's a stabilized or not stabilized, how powerful, and you can probably expect. So quantum information along this line is also an interesting measure. Again, I think it's impossible to use TD bar, many TD bars to quantum computer. But this information there, it's a system information in connection with other atomic systems. So that's the reason. But therefore, from there on, then we get into the collider data. So here, indeed, so we have a large number of the quantum systems produced at the LHC, and of course, similar to the diphoton that John Bell first proposed to test the Alice and A and B, Alice and Bob. Well, of course, we also have a large number of diphoton events. Higgs, and you certainly can calculate the Higgs is a diphoton, but there are even many other channels. TD bar is the best. The TD bar, of course, all the fermions And the leptons, you cannot measure the spin because of our detectors. So our experimental colleague detects so poor. They are unable to do electron polarization, sure, sorry. And they are able to do muon polarization, sorry. Tau barely, but top part is the only one that you can follow the decay so that you can keep track of this, not only one, tau is another possibility. So only these two heavy fermions will be able to infer the spin. So therefore, top part was the first issue that people get into. So we tackle this problem, but we immediately realized we are inferior in the sense to compare with the AMO experiment. AMO experiment was very much like John Bell suggests. You put decide what you actually want to do. No free will. We decide where to measure. But our LSC data, so TD bar, it comes from anywhere. Boom. When space time x and t, we have no clue. The second term may decide to decay later. We decide to decay earlier. So those things are not quite the same level. That's why I said intrinsically we are not testing EPR. We are unable to test EPR. So that's fine. But averagely, with a large amount of quantum ensemble, we calculate, we measure at the very end, same of, because quantum mechanically you are measuring the large quantum ensemble anyway. You are averaging over everything anyway. Even statistically, quantum mechanical prediction. So it's not an able prediction, it's time. But averaging comes back. But how about the different angle, different phases of that activation states? Because each event is different from other event by a weakener. Because you define the top of before the spin and the helicity coordinate. And the second next event, the helicity event is not like an AMO experiment set up. We just pick. But here you have to average over. Then you have to prove your quantity is invariant under your kind of weakener rotation, or so on and so forth. So there was some subtlety to handle the data, but now it's understood. They understood doing the averaging, watch out the averaging carefully. We're able to predict the original quantum mechanics predictions anyway. So then so there are different frameworks. Okay. So this is the one. So there's there are two approaches I would comment on this. So this is the quantum state we want to study. We have a TT bar produced. TT bar produced with the entangled system, hopefully, and we can construct the bipartite TT bar system of the density matrix. And we want to calculate and measure the Cij so that we have a full quantum information. But there are two ways to do that. This is the state we want to study. One way is to keep track of decay. As I said, you follow the top part decay to see the decay products and reconstruct the top and infer the spin, infer all these properties. That's one way. That is standard way. But it's another possibility because you produce this state. The state is produced by some quantum state as well. Gluon, QQ bar. You also can predict how the top quark is produced from the initial state. And there's all kind of information there as well. So in principle, you can do either way. But this way is more traditional, but this way is simpler, but you have assumption part of distribution functions, and so you need to have some additional assumption, but it's certainly work. So the whole point is that either from initial state or final state, you come back, reconstruct your estimation for TT bar system anyway, even by this. Once you reconstruct this, we achieve this tomography and to dig out the correlation and quantum. Okay. So then I will be quick about the formalism. This formalism with the straightforward and basically Pascal and Schroeder to calculate the matrix element so far at the tree level, and you decompose that into the decay. So then and then therefore you cast this decay into the polymatrix. You cast it into this this is sigma aj. One is the one spin operator. The other one spin operator. Here you decompose according to the solid angle distributions, and then you can track these angular distributions, and you can track the asymmetry. The asymmetry reflects this correlation. And this CIJ is one that I call this correlation matrix and this tomography. So you can extract this from measurements. So that's the and then you can even look into the two pieces of the contribution, group contribution, group contribution. It turned out that there are two regions that you have a significant correlation. One is near threshold. It turned out the near threshold is almost like at the rest, and it's basically dominant by the singlet, by the TT bar, the spin singlet. But then you have some, I mentioned your singlet may have some significant correlation, and that is entanglement Doppler problem. But here it's a very, very fast, highly boosted TT bar with high invariant mass. Beta is this invariant mass beta is basically this velocity. Here is the relative angle. Here is a highly boosted region, and that is essentially the triplet. So triplet contribution. You can even map into our prediction and so on and so forth. So then threshold lower events, but near threshold is the high event near the plateau, but low sensitivity because the singlet is not very pronounced. But at high invariant mass range, you suffer from low rate, but the correlation seems to be strong. In any case, there was observed. It was observed by both. In fact, now both are CMS. In fact, I was last September was actually so they measured some quantities that we construct there. They found this well inequality was not quite statistically sensitive yet, but entanglement they say the concurrence quantity was observed already. Okay. Well inequality sensitivity was not reached yet, but in any case they are able to do this. So I quickly flash into two approaches. One is an expression we calculate this approach to from the production, and this production aspect is much simpler because you don't need to look at the top product decay anymore. You make the connection with the production, with the glue fusion, and this mixed states from glue fusion and convoluted with the PDF. And you have a QQ bar annihilation convoluted with PDF, and then you can simply use the only two to two kinematic variables. One is invariant mass, give you the speed. One is the polar angle. Only the two process only two independent. So your information can be monitored by this. But this, of course, you need to have a connection with the central prediction anyway. So you need some this prediction. Then you are able to decompose and calculate everything. It's a very, very simple impression to fit, to compare with your measurements. So that was the one I want to go rather quick. I want to hit the point that because you don't need to rely on the decay, you want to use the production without decay. That is similar for the top part, and the data treatment will be also similar. This will be the observable violation, variable violation. If this quantity is larger than 2, that's a violation. This concurrence larger than 0 is entangled, but the treatment will be much easier. Furthermore, what is better? Because we don't need to look at the decay anymore. You can look at the stable particles. So therefore, you can measure this the mu plus mu minus very nicely, plus minus very nice, as long as you can go back to the production mechanism. But this is easier. The Z pole so the large data sample comes from Z decay. So in principle, if you use a different approach using the production approach, you don't need to follow the decay. You only need to correlate the production. Of course, and then you can fit with the data. You can fit with the measurements anyway. So here is an estimate. So then you really have the sensitivity to see the valve durable and the concurrence durable very nicely. And then some colleagues, the other CMS colleagues are doing this. But in any case, this can be even generalized to any arbitrary processes, including lepton colliders. Lepton collider would be even cleaner. So I would and get into the last part. I think that's also very important. As I mentioned, this the two-level system does not have to be the speed, the easy flavor. In fact, the flavor system was known even earlier. In the 60s, Gilman first the primary tried is a quantum mechanical two-level system oscillation. So the KK bar mixing, in terms of this, the oscillation of the Gilman first wrote down how to systematically treat this KK bar mix. But of course, now we know the KK bar mixing, BB bar mixing is so rich physics to test many things beyond our simple quantum mechanical behavior, including CKM matrix, CKM matrix elements and CP violation and so on and so forth. But the quantum mechanical prediction there is intrinsic, built in. Once again, this is the quantum mechanical test, no classical correspondence. But once again, I said principle, if you two close by level systems oscillate back and forth, and similar to neutrino physics as well. It's quantum mechanical behavior to begin with. Now the question is whether you can formulate this according to this the quantum tomography to dig out the full information and dig out further quantum information in this system. That did not exist. So I think this in the next few days we're going to send out the full construction, and so the piece by piece measurements exist as we know, but there were even two. Let's see what. Yeah, this was one of the early papers by Bell in 2007. They tried to make the oscillation measurements. So here is oscillation measurements for this delta t from first decay to second decay, and because of the lifetime, they only can see one lifetime set oscillation set for B sub D. Okay. Then they fit with the quantum mechanics and the model process. So that's why they extract all the other CKM matrices and so on and so forth. But however, they put in this the so-called decoherence modification. It didn't seem to fit. Therefore, they claim they exclude the decoherence, and they put in one the hidden variable model. They put a hidden variable model. They call this the Pompley salary hidden variable model. It did not fail. So therefore, their paper claimed quantum mechanics check. So it's a relatively primitive calculation and prediction anyway. But that's the first. It's not surprising, right? So they will set up their measurements for this BB bar B sub D oscillation agrees with the standard model with the quantum mechanical oscillation prediction, and exclude the hidden variable modification and exclude the decoherence model. So it was a good one. But so what we did is that we formulate this the decay as well as the oscillation form. So then we define this flavor along one particular direction, we call the Z direction, and the oscillation between this, the Z direction to change from the flavor into flavor combination, give you the XY direction. You can the flavor has no spatial XY direction. It's just the time of flavor. However, you can imagine that the B flavor, the other flavor corresponds to one particular direction. And one. But if you rotate into the other place in this block vector space, block is a sphere to give you any particular point, give you the combination of the two states, and you can even define your flavor along the other directions, such as XY direction in this block vector space. So then it so turned out the oscillation around this direction, around the direction, give you the measurements with XY. But that's not enough. You only have two directions. And then if you also follow the decay, that change the magnitude. Because it's an open system. Change the magnitude to give you the measurement for the third direction. So therefore, combination of oscillation plus decay would be sufficient to fit the three directions that to achieve this fourth problem. So that was the formulation we did. So therefore, so let's so you can calculate the prediction, and then you can use this decaying to do this, and you use the decay into the flavor eigenstate, flavor non-eigenstate to give you the three directions, and you can go on. Let's go to this place. So here is the full story. We construct the BB bar oscillation according to the same formalism put the B flavor and also mixing B and B bar mixing, and then you can calculate this decay and also the oscillation quantities, and you compare with the data. So here, two examples. So turn out you need to have a sizable. That's my problem. So this is B sub D. B sub D has a certain. I will comment on why. So you have this quite a few cycles, but K long and K short decays real quick. So even within the one the decay cycle, and the motor events will oscillate almost like a quarter of the period and sufficient to be tracked. So it so turned out these two systems, B sub S and the K long system are the best system. B sub D is rather poor. B system is in turbulence just because of these quantities at the subtype Y. Yeah, so this is quantum information. We calculate this quantum information coherence, the Bell inequality, the discord, and so you can see that these those quantities you can track to compare with your standard model and also compare with the quantum properties. So Bell inequality in this form is larger than zero, so B the Bell inequality violation. If this is the coherence larger than zero, means in this system it's a so these two systems have this very nice property to be able to do the entanglement inequality violation, and we can even go on to calculate other quantities according to the quantum information. This part I mentioned already, measure the information versus the classical and the quantum mechanical, and the magic measures quantum computing stability. So you can construct these quantities. Once again, we don't mean that this is system to build a quantum computer, but tells you some features. This system contains system. Okay, so why this B sub D is no good? Because you need to have this large oscillation. That's a delta M. And you also need a settable decay. It's a delta gamma. Delta gamma is the system decay into two different mechanisms. So turn out that only the B sub S system has a large the oscillation. You saw the oscillation many times already. It's basically the frequency, and the order one decay to give you the measurement. Ion system seems to be reasonable with order one oscillation and order one decay, but the D system is very very small. You just don't see the oscillation at all. And here, the B sub D system, the oscillation is not too bad. It gives you once a cycle, but the decay is too small. You don't have additional information. These two systems won't be able to construct the tomography. You only have one particular measurement. And B sub D, they claimed because the oscillation is okay, and they claim that the Bell inequality can be tested, as in the previous paper I mentioned, 2007. But no any other elements, because the other elements are unavailable. So the best systems for the whole system we know of B sub S and chaos system, according to our formulation. So this, I think that's it. Okay. So I think we're running short of time. Let me make some comments. So on the one hand, you need to have a large quantities here. B sub D is a 3 orders of magnitude data, and B sub S you have to set on the proportional 5s. But they still have a 10 to the 9, 10 to the 7. I think they have a 10 to the 7. B sub S exists 10 to 7 data. They all exist already. It's not our future prediction. So it's just the analysis have been done this way yet. So the 10 to the 7 B sub S from Bell exists, right? And for chaos system as well. However, B sub S, we want to do this everywhere at the LHC. So the B sub S can be produced at the LHCb in the other CMS as well. But how do we know what kind of a data sample the B sub S, B sub S bar are correlated? Actually, it's very hard to understand. So that gets into the QCD aspect. We probably need to see where and how we can produce this one with certain constructible quantum system. This bias is well defined, just similar to the Higgs decay to anything. It's well defined. It's at a spin 0 to decay, and the quantum state is well defined. But for the other hadronic productions, like B flavor hadrons, then we need to understand the QCD better. But we claim this is a good thing because you may be able to use these measurements to see whether your prediction is a simple quantum mechanical or there are some decoherence. Decoherence means that at production, these B sub S bar are not coherent to begin with because of other gluons, other production mechanisms. But we don't know the fragmentation mechanism anyway. This provides a possibility to fit with the fragmentation mechanism. We can use the fragmentation formalism to see whether it's the same as your coherent system or not. So this additional information, so-called quantum information, provide additional piece of a connection with your production mechanism, as I mentioned, even to test your production understanding. So overall, I think it's interesting to get into that. Well, I haven't talked about CP violation yet. CP violation is small, in particular in chaos system 10⁻�3. But that 10⁻�3, we have a lot amount of data sample. That 10⁻�3 may be sensitive. In particular, what if you find a new CP source? If there's a new CP source modified, it's more than just a standard model one. It will show up in our fitting, in our quantum mechanical fitting because modified the state already. You may remember that the CMS had a hard time to fit it, but they claim that near the threshold seem to have additional. If you do have additional, your fitting would not be as simple as standard model and you see to violate fitting. And these the CMS claim that we may have some kind of bound state near the production. That's pretty cool, right? This additional observable give you this. So overall, so that's I think the quantum experiments produce a large number of events, large number of quantum events, and it's a natural to dig out this the data to see what the quantum information we can construct. I really don't mean to test the EPR at all. That's a wrong conception. And I don't mean to test the quantum mechanics. We accept quantum mechanics, okay, period. We accept quantum mechanics, accept quantum field theory, but dig out quantum information to see what we can learn. DSM, additional CP, or some quantum information that we learn to guide this quantum computing and stuff. So that is the entanglement with the observable already at TD bar system. Well, observable is not yet. Any of the other quantities in lot of our as the CMS colleagues digging into this. I think that's why we call this increasingly interesting aspect. There are two ways. One is to follow the decay. Other way is to try to treat actual production. So from the kinematics. And the flavor is in addition to the existing the spin analysis, and the flavor has a very rich rich physics and a lot of data and much to come as well. So hopefully we can understand the quantum correlation and maybe even connection with a modification such as from BSM and so on and so forth. And there was so we even timely submit one to the European strategy update. Say, hey, don't forget about this. It's nothing really worth taking, but this is additional information we probably should not forget. It was submitted to the European strategy. It was in already. Well, so quantum information science is with us. Quantum information science is there in the climate. Even Alex data. It's natural.
Thank you for the very nice talk. Any questions in the audience?
So it's a less well-posed question, but I wanted to ask a general formal statement about IR safety related to your fragmentation question and jet formation or soft collinear effects and non-asymptotic states. So I understand that you can formulate the amplitude structure at 2 to 2 with spin decomposition and Z coefficients.
Yeah.
But given the fact that we measure IR safe observables, we will bleed into long distance collisions.
So far, the formalism we presented, including both the spin correlation and the flavor correlation, are based on treatable results, which is true. If you only consider loop corrections, it won't change the states. But if you include the radiation, you're absolutely right. Not only the IR safety, but also if you have additional gluon to radiate off, your state will have to be reformulated. So in principle, that is an additional thing that probably we can call this a decoherence effect. So decoherence effect was not taken into account. So similar to my comment toward the end, that is a good thing. We can compare with our measurements. And so far, the top box system seem to have a very little decoherent event, to my surprise. And it's a pleasant surprise. So it's a T-bar system they measured. They measured very similar to the simple tree-level prediction. That means that the decoherent effect does not seem to be the dominant effect. But if it does change this, I think that's important information we should make use of that. We really cannot claim our prediction is totally robust because we ignore the potentially sizable, maybe dominant decoherence effect. We did not. The TD bar gives you some confidence.
Some rough idea from the information of circles, what kind of PSM, like recoupling on strong bias precedence. So
Yeah.
based on
Definitely. So exactly, very good point. You can do either way. You can do that. Give me a particular BSM, such as the example we talk about this the TD bar threshold and TD bar threshold near the threshold. You could have some kind of a TD bar resonance. Eta T because glue dominance. Glue dominance is not going to be J side, not going to be spin 1, spin 0, and pseudo spin. So you can toss into this one, and it was even analyzed to fit data pretty well for pseudoscalar Higgs. Pseudoscalar Higgs in that mass region will give you the correct one. But of course, you look for other channels you can find. You only can say that pseudoscalar Higgs does not seem to be real. But if there were a pseudoscalar Higgs in that particular region, that would give you the correct fitting. So you can see that that is an interesting example to answer your question already. On the one hand, you look at our standard model prediction to compare with data to see the deviation. On the other hand, give me a particular model. We could include this additional BSM contribution to that. And the example would be summarized Z prime, give me a Z prime. I would be able to predict additional thing to on top of the other one. So it's similar to the other BSM searches. It's just a new correlation, new observable. In terms of search, it's somewhat similar, one way back and forth. Yeah. So either direction, let's see, yeah. But you certainly can construct. Yeah.
I'm very nice talk. One thing that I think probably I didn't understand, you made a statement that in the case of TT bar, saying, oh, it's different than the Bell-Duncan experiment with the 2 photons because you say, well, I don't have information about the time. I don't understand. I mean, you said you don't have the information about the space-time point where the why not?
Yeah. Let me repeat.
I mean, you have this event with only 2 tops, so you know that they're coming from the same vertex, and you have the time.
Yeah.
So what's missing?
Yeah, let me answer slightly differently to see whether it helps. So sure, when you look at your muon and a B, you see this from with the B final state and the muon in the missing energy seem to be from a top. Okay, then you measure where the muon is a particular angle or something. This event does not specify the top speed on event by event basis. You are measuring the classical observables. We are measuring classical observable to infer the speed. Okay, then you wait for the second top. Sometime later, at a different place, you see another top, T bar. It's a B bar and muon plus. You see that's another one. But you measure the angle. You even don't know space time and you measure the angle. You say, I infer this is a spin at the top spin. You calculate everything, you average over the spin, the distribution. After a million events, fit our standard model, fit everything well. That's what other CMS did. But in comparison with the AMO events, they have one detector. I would just want to say, well, I can't here anywhere. Fix that. Fix the second one. You measure the first one, the correlation, and you can infer the other one. It must be. See? Yeah. At production, it's absolutely fixed. At speed point. And but at the measurement, you're not measure the complex speed, you measure the observable field complex. We infer that. Intrinsic, even for the flavor. Even for the flavor, of course, not space-time, it's a time, it's time. But you still, when this guy decays, you know at that moment what the other what the other flavor must be. But you have to wait until that second one decides to decay and decay to some distribution, and you fit. You fit, after fitting, save. But so that's why Einstein was upset. I said there was a hidden variable. Someone fixed that at you. Of course, your distribution is right. The hidden variable makes that happen. So that you cannot check against the hidden.
Okay, any other questions? Okay, if not, then the next thing. We'll reconvene at past.